All right, so is that better? All right. So I should be getting up before I leave today. Kind of a similar thing for your Connect and individual assignments as I did for iClicker, where I'll be putting up what your lowest grade, what your grade is with the lowest dropped. So that should pop up there later this afternoon. That'll give you a little bit better idea, kind of filling in that, figure out your grade tool, kind of what you need on the final here. I will, I think our exam isn't till next Friday or whatever. A couple of you have kind of scheduled to take it early. Yeah. I think this one's noon. Is it? Okay, I was gonna say it's in the syllabus. But yeah, noon to 2. So I will, if we don't get through all of this like practice exam problem stuff today and Monday, I'll film a video kind of Tuesday and put that up there of me working through whichever ones we don't get to. I think we'll probably get through most of them. But just in case, I wanted to mention that. Other than that, any other questions for me? If you have specific questions over either of the practice exams or just like in general, something maybe that you didn't see on the practice exam that you had a question about, I can kind of start with that first. Otherwise, I'll probably kind of pick and choose. 2? Okay. So we've got kind of the setup is that we are looking at McDonald's before and after calorie consumption, right? So we had like this difference variable created. We then found the mean difference, the variance on that difference variable. We got a sample size of 42 people, and we have a what type of tailed test. So if we look at the alternative, the null hypothesis, we always look at the alternative for what type of test. We've got a less than sign, so it's a left-tailed or a less than test. So we're asked to find the critical value, and we're given an assumed true test statistic. So one thing that we know is when we're thinking about the distribution of our sample differences, right? It's going to be centered around that assumed true difference, which we have as 0. Excuse me. We found -50 as that sample difference. So when we're thinking about what distribution we want to use, well, all we have is this sample variance. So we're using the student t distribution. This is going to translate into some test statistic, right? This -50 will become some test statistic. But before we do that, we want to find the critical value that says this is the threshold number of standard deviations away that we could see sample evidence be. Anything past this point will reject that null, okay? So for a left-tailed test, it's going to be the critical value that gives me alpha in this tail. So I know that the critical value should be negative. So right away, I could rule out what? D here, because I know for a left-tailed test, it has to be a negative critical value. Okay. From there, I know it's going to be a t value. I think the alpha was will be 0.05, I think is what this problem told us. The other thing that we'll need is our degrees of freedom when we're dealing with a student t distribution, right? So the degrees of freedom when we have this mean difference, I said it's almost like it's easier. It goes back to like it's a one population example where the degrees of freedom is just n-1. So our sample size was 42. So our degrees of freedom should be 41. Okay. So we'll go to that t table. We wanted 0.05 in the tail at a degrees of freedom of 41, so 1.683. However, the student t table always is looking at the right side of the distribution. We wanted the left side, so it's going to be that same value, but negative. Okay. Yeah.
So you know it's a t distribution because it's a sample? Is that what it is?
So it doesn't have as much of a bearing on this exam. Oops, that's not what I wanted to do. Why did I do that? But if we only have sample variances, we always use the student t distribution. So the only types of examples we'll have on this exam, we've got that mean difference, and we only have a sample variance. We're also thinking about, we don't really do it as in detail, But with our coefficients, we have these standard errors, which really, if it's easier, you can kind of think about it as it's like the standard deviation of these coefficients. So we always use that student t distribution for these. Why is this so? Does that show up a little better, right? So we're always using the student t. The only time we use the standard normal is when we had proportions or we had means where we knew that population variance. We're not dealing with anything from this exam related to that, but yeah.
Thank you.
Yep. Oops. So that's if we wanted to do a confidence interval, right? So if we wanted to build a confidence interval for like the true values for what this mean difference are, this would be the equation we use. The critical value is the one that's part of that hypothesis test, and we find that critical value, which represents the kind of threshold number of standard deviations away that we could go. Any other questions? I didn't completely finish it, right? Because I found the critical value, but I need to know if I reject the null or not. Well, for a left-tailed test, right, my rejection region would be the area to the left. I think the test statistic I said to assume that you found was negative 2.5. So that one very clearly going to be in my rejection region here. Okay. Any questions on any other questions on this one specifically? Any other questions that you wanted to go over before I kind of start picking and choosing and jumping around here? Or just even general ideas or topics? Okay, so what am I going to go over here? We could review kind of this problem number 3. Wasn't really given to you as like a multiple choice, but we can kind of think about maybe how I could turn it into one, right? So I'm looking at this output and I had kind of the gender and the smoking status of the individual. And I did a very poor job in this practice exam of specifying until the problem that this was representing the BMI of people in these categories. Okay? So these values are like the average BMI for males who never smoked, for females who currently smoke, and all the different combinations. So whenever we had these kind of averages given to us broken down by 2 factors, this is where we could do that 2-factor ANOVA. Right? So even though it's group data, I can start to see, does this variable of BMI vary with one of these factors, either gender or kind of smoking status of the individual? So what can be said about the variation at the 95% level? I probably wouldn't leave it as open-ended as this, but I might say something like, at the 95% level, which of the following is true? And then we'll have different combinations of there is variation in BMI with respect to gender, but not smoking status. There is variation in respect to smoking status, but not gender. There's neither variation in neither of them, or there's variation due to both, right? So maybe kind of those 4 different combinations. And the way we determine if there's variation coming from these factors, right, in our row and our columns, is by running this 2-way factor ANOVA and then looking at the p-value associated with the row variation and the column variation. So here, our null hypothesis is that, kind of floating around in the background, is that all these different groups, so, you know, we could call this, male smoking is the same as male never smoked is the same as male. Like all these are the same. We're starting out thinking that there's no variation in any of these groups. So if we can get a p-value that's less than whatever alpha we've set, we're going to be able to reject this null. So similar to our coefficients from linear regression, we're starting out thinking about there's no variation. Well, with coefficients, there was no relationship with the y, but here there's no variation. So if we can reject that, we're saying that there is variation, right? So if I look at this Anova output, what can I say about the variation in BMI with respect to gender and smoking status? So I look at those p-values. Is there variation in BMI across the rows? No, I can't reject the null So I can't reject that there's no variation, right? And alpha would be 0.05 here, right? But it doesn't matter. Our p-value is enormous. What about, is there variation with respect to the columns? No. So I would say here, the 95% level, I don't find any evidence that BMI varies with smoking status or with gender, right? And it's actually even a little bit more powerful. I would actually be able to say they're holding constant gender. There's no variation in BMI with respect to smoking status. Holding constant smoking status, there's no variation in respect in BMI in respect to gender either. Okay. But maybe on the exam, I give you something a little bit more interesting, like this, right? So now looking at these p-values, there's no variation in BMI with respect to gender, but at the 95% significance level, I could reject the null, right? 0.04 would be less than 0.05. So if this was my p-value, I could say that I did find that there was variation in BMI with respect to smoking status. But with the numbers given, there was no variation. So really when it comes to this Anova stuff, if I put something like this on the exam, which I have it written, so I kind of know what's on there, I would not make you run this Anova, but I would give you output that looks similar to this, right? Maybe give you what the original kind of row and column headings were, and then give you that two-way factor Anova output, which really you're just using the p-values there. If the p-values are less than alpha, there's variation in respect to your, y or your BMI variable here in the rows or in the columns, right? Depending on which, if either one of them have a p-value less than alpha. Any questions over anything or what, anything else? Like, what if, would you do this or could you do that or would you ask this or anything like that? Yeah.
So I guess in a specific problem, it says variation significance, or is that like
so you are saying that there's variation at that significance level, right? So for, if I had this p-value, which was 0.04, I would say, at the 95% level with 95% confidence, I could say there's variation in respect to what the column, so in respect to smoking status. But I'm probably going to ask it in the way of, is there variation? Because I want to connect this idea of, yeah, we can make our rejection decision. Like, I don't think that that's probably very difficult for you at this point, like comparing the p-value to alpha. I mean, that's not that hard to begin with, but we've done it so much at this point that we know we should be rejecting. But what are you rejecting? You're rejecting that there's no variation, right? Which is really saying you found evidence that there is significant variation, or there's variation with a certain level of significance, right? 5%, 10, 1%. Yeah.
Are you going to ask us to do anything on the Anova output except aside from the p-value?
We never use any of the other stuff in class, so I wouldn't expect you to do that. No. I mean, most of this stuff isn't that. Thank you. So most of this stuff isn't that interesting, right? Like I said, that there's really a different distribution, like a F distribution going on, but it's a nightmare to, I don't know. It doesn't really help us to understand more about it. What really is important is that we know we can get these p-values, which tell us about whether or not we can reject it. Any other questions there? Yeah. Yeah, so that was this stuff here, right? So the match pairs is really like the only like old kind of hypothesis testing stuff that we did. So we already talked about finding critical values. We look at that formula sheet. Here's that test statistic for matched pairs. Here's how we find degrees of freedom for matched pairs, and here's a confidence interval equation. I probably would ask you to find the test statistic. I'll probably ask you to find a critical value and make rejection decisions. But it's probably about as far as I'll go with the matched pair stuff. Any other questions here before we keep moving? Okay. So that kind of gets at some old stuff. And then here's probably some more simplistic kind of newer things, right? So I would say like what we'll go over today is too terribly tough for the linear regression. And then that other practice exam, which we'll go over on Monday, that has some more of the more nuanced stuff that we were doing with regression, right? But I'll make sure that if we have time today, I kind of mention some of those things as well, so that I prepare you guys. I want you guys to do really well. So how would I interpret the coefficient on education here? So I've got wage as my Y variable, or my dependent variable, and then I included education, experience, age, and gender. This is really small, even for me, so let's try to make it a little bit bigger, right? So how would I interpret that coefficient for education? So before I even look at the possible answers here, how would you interpret that education coefficient? So the general form of the interpretation is a 1 unit change in my X variable causes the predicted Y variable to go up or down by whatever that coefficient is. So here, how would I interpret coefficient of education? Yeah.
So with an additional year of education, the wage will go up $1.23.
Yep. So probably more like to say it's correlated with a wage increase, or the predicted wage increase is $1.23 higher, right? And the other thing that we have to add, the kind of caveat, when I've got more than one variable on the right-hand side there, holding everything else constant, right? So holding everything else constant, every additional year of education is correlated with a $1.23 increase in hourly wage. What if I wanted to interpret that gender variable? So I think I stayed up here. It's a 1 if the individual is male, 0 if not. So how would I interpret the coefficient on that gender variable? So now my 1 unit change, right? Well, that variable is just a 0, 1. So it's going from the 0 group to the 1 group. Right? So a male, yeah.
So it's going to be saying that basically like a female compared to a male, that difference is expected to be $2.29 higher.
Yep, with the exception of here, and usually I do put this as kind of female because we were looking at discrimination stuff, but here the 1 actually indicated male, 0 is female. So it's literally exactly what you said, just the increase would be for males as opposed to females, right? Which would kind of fall in line with like what we might expect to see with like discrimination or something like that, right? So we've got about $2.29 higher if the individual is male relative to female. I said that very nonchalantly, like it's not a big deal, but I mean, we just like, we know that this, like, usually when we're comparing wages, that in the data, they tend to be lower for females and males. Now, if you control for like the job type, we didn't get to go into too much of that, which is sad, but if you actually look at a lot of the regression analysis that's been done, we talked about emitted variables. So if I just run like a regression like this, I usually pick up that like males have a positive coefficient. However, if there's any differences in kind of, let's say I was looking at starting salaries of everyone at Ball State, and I ran a similar regression, I'll pick up a positive coefficient on males. But what's maybe an important omitted variable that would be biasing that coefficient a lot if I have differences in potentially the major choice, right? So I had a slide from my 201 class. I won't waste time since we're doing review, but this kind of fits in that if you look at like all the engineering majors, right? And maybe this is more of a product of like, they're not inviting to females, but the percent of females in engineering majors is like 15, 20% if you're looking at different types of engineering. Some of the other like CIS majors that are higher paying kind of starting salaries tend to have a lower percent of females, while things like primary, like elementary education is like 90% females if you look at the like who's in that major, right? So if you have differences in major choice, that's going to be correlated with kind of the gender variable and with the starting salary. So you're going to have a really biased coefficient. And if you can include controls in for that major choice, it still would be positive here. It still would be that males have a higher starting salary, but the size of the effect is greatly reduced, right? So it's starting to think about these omitted variables and how they play a role. All right, I a little aside there. So this kind of a problem is me trying to give you points in this exam, right? If you go kind of or here in class and you're looking at a practice exams, I left kind of put this white box over the test statistics. But if I wanted to calculate the test statistic on age here, to find the test statistic for my coefficient, all I do is take that coefficient estimate and divide it by its associated standard error. So if I'm looking at this variable of age, negative 0.019 divided by 0.08. It's going to be approximately -1/4. So I'm guessing the exact value here ends up being -0.229, right? So all I do is take that age coefficient and divide it by the standard error associated with that coefficient. And I could do that for every single one of these variables if I really wanted to. That might be some good practice. I mean, like I said, good practice, but I think most of you, this is probably going to be, hopefully everyone gets this question right. Like I'm expecting no one to get this one wrong. Okay. Does that make sense? Any questions on that one? It shouldn't be too tough. Which of the variables in the above regression would we say, other than the intercept, could you reject the null hypothesis that there's no relationship for, right? So this problem kind of reminds you, we're starting out assuming all these coefficients are equal to 0. So that means that there's no relationship. That's where we start out. Stack the deck against ourselves, assume that none of these variables we included are related to wage at all. If we can find a p-value less than what? An alpha of 0.01 at the 99% level, then I could reject this null or say I found evidence that there is a significant relationship. So which ones can I reject the null for here? All I do is go to this p-value column and see what p-values are less than that alpha of 0.01, right? That's all I have to do. So education, that p-value is less than 0.01, so I reject. Experience, that p-value is less than 0.01, so I can reject. For age and gender, they both have p-values above 0.01, so I would fail to reject the null. So the only variables that I could reject the null and say that there actually is a significant relationship between these two variables and wage would be my education and experience variable, right? So I think if I go down here, that would be C. Okay? So all you're doing there is comparing that p-value to alpha. If it's less than alpha, you can reject that there's no relationship, or that slope would be 0. Said differently, you're saying there is a significant relationship if you can reject that null. Okay. Other questions there? So this should be some of the like easier linear regression stuff, I think. Let's say I gave you a problem like this. We were trying to predict GPAs from SATs, right? I'm kind of using similar examples as we've done in class, just so we can really, doesn't make it too much harder. And I end up with this intercept value being 1.5 and the SAT coefficient being 0.002. I give you the standard errors here. I probably won't do something like this. At one point in time, I thought maybe this was be something, but if I've got my standard errors and my coefficients, how would I find the SAT for that slope coefficient beta 1? All I would do is take my coefficient of 0.002 and divide it by that coefficient's associated standard error, right? So 0.002 divided by 0.00075. Is it 2.67? Anybody want to help me out with the math? Yeah, math in my head there. Yeah, we should get about 2.67 there, right? So all you do is take that coefficient and divide it by its standard error. That one should be easy. Okay. If that intercept was 1.5, how would I interpret that intercept? So before we even look at the answers here, because I will have, I think the exam is 17 multiple choice questions and 3 short answer that have kind of multiple parts to them. And it's about a 60-40 split in terms of the points. 60% of the points come from the multiple choice, 40% from short answer.
My question is like, how many points is each individual?
Let me see if I can remember. So 17 times whatever gets to be around 60, right? So with 4.2, no. I've done multiple exams here. So someone help me out. 60 divided by 17 is what?
3.5.
3.5. So they're about 3.5 points. Yeah. So yeah, 3.5 points, total of 60 points there, and about 40 points to the short answer. I think technically there's more than 100 points available. So like 102 or 103. So you could like, I tried to make it so you get like one multiple choice wrong. If you get everything else right, you'd still get 100. Yeah. So I think about this intercept value coefficient of 1.5. How would I interpret that intercept? Yeah.
It would be for this one.
Yep.
It would be B, I believe, because the intercept is telling you what expected GPA would be when they have no SAT score.
Yeah, right. So once I have these values, so if I'm thinking about writing out my prediction equation, so I'm going to try to make predictions about GPA, and I'm just plugging in my intercept coefficient and my SAT coefficient, right? So if I plug in different values for SAT score, I can come up with a predicted GPA for that person, right? The interpretation of our intercept would be, if our X variable is equal to 0, this is the predicted value for our Y variable. So if someone got a 0 on the SAT, we would predict their GPA would be 1.5 in college. Right? Now, if we add in more variables, the only change to that interpretation of the intercept is if all the variables are equal to 0, the intercept is the predicted value of our Y variable. And sometimes when we have multiple linear regression, that gets kind of weird. Like we get some weird interpretations, like people who are 0 years old or have 0, these other things that just don't make a lot of sense. But you almost think about it, we only see the data up here. When you're drawing that line of best fit, it does have to start somewhere, right? Even if you never see that X variable take on values that are that low, it does start out kind of wherever that X variable is equal to 0.
I would like playing with that a little bit. So I know with a lot of the multiple regressions we've done, we've had like 0, 1 variables, like for like male to female.
Yep.
So in that instance, if it was a 0 and it was just describing if you were a male or a female, how would that work?
Because you don't really have a line of best fit.
Yeah.
So if you were to simply run like a simple linear regression with just one variable on the right-hand side, and all that was a 1, 0 variable, it's really weird. All you'd really be doing, you don't have a line of best fit. What you'd be picking up is just the difference in starting point. So it's almost like you'd be running like 2 intercepts. But yeah, it's kind of weird. But I mean, in practice, you always include several other variables. And so then what that tells you is, right, there's like whatever the relationship is between these other variables X, it's just shifting your intercept from belonging to the group it's a 1 relative to a 0. Yeah, there's not a great visual. Like I said, you're really just moving the point here. Yeah. Actually, what you're really doing if you do that is you're just picking up the differences in the average between those two groups. That's all you're doing if you just included one dummy variable on the right hand side there. Any other questions? Those are good. So we had what? Yeah, the expected for the SAT of 0, the expected GPA is 1.5. What if I had a student who scored a 1200 on the SAT? What would their predicted GPA be? When it comes to kind of making predictions, this one I kept made easy because we only had one variable. All I would do is plug in that hypothetical person's SAT score. So after Monday, after the due date is passed on Tuesday as early as possible, I'll put up an answer key to that 4th Excel. That would be some additional good, something good to go over because it has some questions in here where you're making predictions and doing some other things. So you could have more than one variable here and have to make a prediction, but all it would be is plug in your coefficients and then plug in the X values for this hypothetical person. So here, 1200 on this SAT, I only have one thing to plug in, 0.002 times 1200. So that would be what? 1%. So 2.4. Is that right? Okay. I never claimed to be the best mental math person. So this ends up being 2.4, adding the intercept of 1.5. And we get this predicted GPA of 3.9. Okay. Any questions there? So 3.9 would be our predicted GPA there. Okay. I might skip around a little bit. I've got 20 minutes. I think I want to come down to this one. So we're going to skip down a little bit. Some of these other ones are a little bit easier. They're really just getting at the idea that we're picking up evidence of a correlation. We can't make a causal interpretation here. I then have this kind of birth weight example where I give you the intercept. We're thinking about mother's age potentially, but I really want to focus on what I think is a little bit more interesting here is what is one omitted variable that could bias your coefficient for the effect of mother's age on birth weight, and what direction do you think that bias would be? So I might do something like this on a short answer question, leave it pretty open-ended. So what we're thinking about here is we've got birth weight. And if we were to run this really naive, simple linear regression where we only include mother's age, then that coefficient that we see is going to include the true effect plus this bias component. So I'll show you where it's at in the formula sheet in just a second, but this bias will be something like this. So here it would be mother's age and some other variable that we left out divided by the variance on mother's age. Well, variances are always positive. So what we can do is think about, is there a variable that I think could be correlated with the mother's age? And if you want to think about birth weight, really think about the higher the birth weight, for all intents and purposes, reflects a healthier kind of pregnancy or a healthier child. Okay? So what's one thing that could be correlated with both mother's age, but also if I included this other variable in the regression, it would have a significant effect on birth weights as well. Right? So what's something maybe that's correlated with both birth weight and mother's age here? Yeah. So let's use that one. It's a little bit, I like that one. It's not continuous, right? It's just a 0, 1, but it's okay, right? So if I think about how would that be correlated with mother's age? As a mother gets older, what do you think happens to the likelihood that they are smoking while pregnant? So the older they get, you think they're more likely to smoke while they're pregnant? What we actually see is like most of that is at really like 16, 18-year-old kids, right? Who haven't been told or haven't heard enough to like know they shouldn't be smoking while pregnant, right? They have lower education levels. So smoking while pregnant, right, would actually have a negative covariance or correlation with mother's age. Now, if you would have told me that you thought the relationship went the other way, I would have just graded that. Like, all I'm asking you is to give me some intuition. If that intuition's wrong, you don't have the data in front of you. I would expect you to like maybe get it right. But if you, as long as you tell me like what you think that relationship is and a little blurb why, okay, right? Like, just tell me what you think that sign is. Then that variable of smoking while pregnant, if we were to include it in the regression, what this one, I mean, if you would have told me the opposite way, I would have graded as correct. But what do we know? I've used it in class 4. What would the effect of smoking while pregnant be on birth weights? Right, it's bad for the kid. Birth weights are a measure of health, so it would push it down. So here, what's the bias that's going to exist? Well, we have a negative times a negative divided by a positive. So this is actually going to be a positive bias. So the estimate that we see from the regression is actually going to be greater than what the actual effect is because it has this positive kind of bias there, right? So when you're thinking about, you know, what did we just do? What direction do you think it's going to bias the coefficient? We used this guy right here. We kind of talked about intuitively going into it, what we expected for that covariance sign to be, what we expected the coefficient, if we included that second variable in our regression, would be, and then kind of put a sign on our bias there. Okay. Any questions on that? Yeah. Yep. So it shouldn't impact it at all. You're really thinking about the relationship. The only difference with a 0, 1 variable is you're not thinking so like with the covariance part of it. It's easier to think about what's, as the mother's age goes up, what's the change in the probability that they smoke while pregnant, right? So if it's a continuous variable, let's say we were just doing, I want my red marker. Let's say we did education level. I mean, this one, what do you think the covariance would be between mother's age and education? As someone gets older, what's more likely? They get more education, right? So you actually would have a positive covariance here. If you include education, what do you think the sign of that coefficient would be? As a mother gets one, additional years of education, what would we expect to happen to birth weights? Like I said, probably healthy. I mean, they have more information on what to do during pregnancy. Potentially they're earning more money, you can buy higher quality foods, healthcare. So there, we actually have a positive times a positive divided by a positive. We still have a positive bias, but like we would just work through a little bit differently. Yeah, it's actually the 1-0 variable is actually a little harder to think about because it's like the covariance represents like the change in the probability we see a 1 versus a 0. Any other questions on that one? That was a good question. Yeah.
So if like, the first one with Smokey would overestimate the birth weight, and then the second one would underestimate.
So both of them, right, actually led to an overestimation because negative times a negative is positive, divided by positive is positive bias. Positive times a positive divided by a positive is a positive bias as well. But we could end up with, let me think of something that would be, so what would be something that might have a positive or negative effect? So you could think about something like, oh shoot, mother's age. If I wanted to do, I don't have another color, I have a black marker. This is maybe not the greatest, but right? I'm using some measure of like weight or like BMI. There, the covariance between age and BMI, typically as people get older, they tend to kind of have a higher BMI. So we would actually have a positive relationship there. However, if we include a BMI in this regression, as people kind of are heavier, typically pregnancies the health of the child goes down. So we would actually see a negative coefficient if we were to include that, right? And maybe we don't use BMI. Maybe we use some kind of different measure of like being healthy. But there, now we have a negative times a positive divided by a positive. Well, now this bias, we would actually see an estimate that's too low, right? Because if we'd have the actual effect plus some negative value, we'd actually see a coefficient that's too low. So you could have, right, an estimate that the bias is negative. This one, it's harder to think of examples why. Like, I don't even really like this example, but it may be a variable where you kind of see a positive times a negative here. All right. Any other questions on that one? So I would expect you to know how to put a sign on the bias and kind of think about, variables that would potentially. Now I'll probably, if I ask you this on the exam, I would give you an omitted variable, and then you would tell me what the covariance is and what you would expect that coefficient to be if you were to include it. I won't be as like mean here and expect you to like come up with one off the top of your head, right? All right. So is there anything else here? I mean, a lot of this is just like more examples. I know there's something else I want to do. Here we go. Let's do this one. No, I changed my mind. Let's do this one. Right? So just after 23. So let's say we've got this log specification, right? And it's height and weight. We did kind of want some of this in class, but it's good to kind of review it and then talk about where we have different examples. So whenever I use a log model, the interpretation, what is taking the log change the interpretation to? Instead of units, we're now dealing with percentages, right? So now the interpretation is a 1% change in my X variable causes the predicted Y value to change by whatever beta is percent. I don't have to move the decimal. I saw in kind of some of the individual assignments, there was a little confusion by some people, but when it's a log model, you don't have to move the decimal at all. So here, a 1% change in height would change the expected weight by 1.3%. right? I don't have to move that decimal at all, right? Everything's just in percentages, okay? That makes any questions on that? So what if instead I wanted to do I'll try to maybe give you a good way to remember this. Start on a new sheet. So let's say we've got the level's easy, right? Everything's in units, log. I don't think it's that difficult. Everything's just in percentages. The kind of trickier ones would be, what if I had log level, and what if I had level log, right? So here, this was kind of my log level, and here was my level log. So I've got the first name refers to my y variable, the second word refers to my x variable, kind of the same order in which we write that regression, okay? So these are our two other kind of combinations we can have. And we know here that we're going to have to do what to these coefficients? Either multiply or divide them by 100. So how can maybe we remember which one's which, right? Well, think about it this way. Here, the interpretation is going to be a 1 unit change because the x variable is in units. So whatever the x variable is in, that's the change you're thinking about. So if you didn't take the log of the x variable, it's a 1 unit change, would change the expected value for y by, well, here I'm going from units to a percent. Think about it as like units are in decimal form, right? So if I need to take decimal form to a percentage, what do I need to do? Move the decimal 2 places or multiply it by 100. So to get my units into a percentage interpretation, I take that coefficient and I multiply it by 100, right? So let's say this was like 0.2. How would I interpret this is, for every 1 additional inch that someone is, like taller that the person is, I would expect weight to change by, when I multiply this by 100, it would be what? 20% increase in weight. I chose a wild number here. That doesn't make any sense, but that would be the interpretation, right? For every additional inch increase in height, the expected weight would change by whatever that coefficient is times 100%. Okay? So I'm going from units to percentages. It's almost just like I'm going from decimal to percentage form. I multiply by 100. When I have a level log, I took the log of my x variable, so that's kind of my percent, right? Log is when we were dealing with percentages. So now it's if height goes up by 1%, the expected change in weight would be, not multiplied by, divided by 100, right? So I'm wanting to go from percentages to units, or like percentages to decimal form, if that makes it easy to remember. Well, if I'm going from percent to a decimal, I need to divide by 100, right? So if I had 0.2 here, that would be like for every 1% increase in height, I would expect weight to go up by 0.002 pounds, right? I would divide by 100, it kind of moves that decimal, okay? So I think that's like, I was trying to think of a good way to remember it the other day. And I think it's like, look at your x variable. If it's in units, think of it as like units would have you in decimal form. So a unit change, translating that to a percent change in y, you're going from decimal to percentage, multiply by 100, right? If I'm going from percentages to units or percentages to decimals, I'll take that coefficient and divide it by 100, right? So that might be a good way to kind of remember which one of those you have to divide and which one of those you have to multiply by 100, okay? Any questions on that? Or if I'm looking at this, yeah, it's probably the best way to think about it. I don't know, maybe there's some way where you know that if the log word is first, that's when you multiply by 100. Like there might be some way you can kind of remember it like that as well. To me, this is how my brain works. But you could just associate like, oh, if it's the log level, if log comes first, that's when I multiply by 100. Okay. And then I might do something on the exam with some R squared terms. So if I'm looking at the R squared here, how would I interpret that? Yeah.
So that about 4.86% of the data is being, or the variation is being explained by our variables.
By height here, because we only have one. But yeah, if we had more variables, it'd be the percent of that variation on our Y variable that is explained by the X or the right-hand side of the independent variables that we included. Yep. What are some ways I could potentially increase that R squared?
Just add variables.
Add more variables is always one way to do it. Now, if I ask you this on the exam, when I ask you maybe are there ways to change R squared? If you say adding variables, more than one way doesn't mean you just tell me different variables, right? Adding variables like is one way, right? What's another way I could maybe kind of look at this relationship between height and weight and get a higher R squared?
You could like do a different like format, so you could go to level or level log.
I could go level log. What's another way I could pick up even if there was a nonlinear relationship? I could take weight as my dependent variable, height as my X variable. What else could I include? It is an additional variable, but a quadratic, right? To pick up that nonlinear relationship. So those are all ways I could kind of increase my R squared there, trying to get a better idea or make better predictions, right, about this Y variable. Okay. I said one way, we listed a bunch, so right, that covers a lot. That's good.
What did you mean by the quadratic?
Oh, so that would be like when we have a quadratic, sorry. Oh, we did weight was our dependent. And we'll go over an example on this practice exam on Monday. But a quadratic was where we just include an additional term, which is that variable squared. Right? So it picks up a slightly different nonlinear relationship than our log models do. Yep. All right, any other questions? We'll talk a little bit more about the exam on Monday. I'll just keep doing more review. One thing that I have a favor to ask of you guys is, if you could, maybe if you just want to do it, stay in class here and do it now, or sometime later today or this weekend, I would greatly appreciate it. I get the emails too. I'm annoyed as you are. Would like if you could get on and do your student evaluations for me. Helps me out. It helps out the College of Business. It also lets me know like things I can work on. I'm sure there's a laundry list, but like I would really appreciate if you guys could kind of get on and do that. Other than that, I will see you on Monday. Have a good weekend. And if you have any questions over the weekend about the exam, feel free to shoot me an email. And yeah, I guess that does it for us today.